So, dear students, welcome back to our online certification course on analog electronic circuits. Myself Pradeep Mandal from E&EC department of IIT Kharagpur. Today's topic of discussion it is numerical examples on current mirror and some application circuits where we are using current mirror. So, primarily we will be talking about numerical examples to complement whatever the theory you have learned on current mirror and its application circuit. Now, according to our plan, we are in week 9 and in fact, that is the course module 8 and we have discussed about the theoretical aspect of current mirror and different application circuits. And as I said that today we will be covering numerical examples extensively on current mirror and different types of current mirrors, including simple one and then advanced one. So, the coverage of today's presentation is enlisted here. So, we shall start with numerical examples of simple current mirror. We may start with current mirror having MOSFET transistor and then we can go for current mirror using BJT and then we will be moving to numerical examples on improvised current mirror or more precision current mirror, and there also we will be having two types of circuits, namely one using BJTs and then other one is MOSFET. And subsequently, we will be talking about numerical examples on amplifiers which are using current mirror. So, our main focus is on the current mirror. So, we may not be going into the aspect of the amplifiers, but primarily what are the advantages we can get using current mirror and what is the corresponding calculation we do, that will be highlighted by considering two specific types of examples. One is single ended amplifier, namely common emitter and common source amplifier, and then differential amplifier. Now, coming to current mirror, simple current mirror constructed by MOSFET. Here we do have the example. So, here we do have the example circuit where M1 and M2 are forming current mirror. We do have a reference current here and then we do have the application circuit here. So, in this example the W by L of transistor 1 and transistor 2 along with the K factor, it is given. For transistor 1 we do have 1 milliampere per volt square. For transistor 2 we do have 4 milliampere per volt square, and let me assume that both the transistors are having equal threshold voltage of 1.5, and then we do have the reference current equals to half milliampere and then supply voltage it is 12 volt. To start with, let me go simpler version, ignoring lambda effect, considering both the lambdas are very small, and let me try to find the values of VGS1 and IDS2. Of course, IDS1 it is same as I reference current, namely half milliampere, but then VGS1 it is setting VGS2, and since the W by L or K into W by L of the two transistors they are different, we are expecting the current here it will be different. So, let me start with the calculation of VGS1 for I reference equals to 0.5. So, 0.5 milliampere. So, that is the IDS, that is equal to its corresponding K W by L, which is 1 milliampere per volt square by 2 into VGS 1 minus VTH square. So, note that for this calculation we are ignoring 1 plus lambda VDS. Even if the lambda is given, we normally ignore that. And if you see here, this equation, it is giving us VGS 1 equals to VTH 1 plus 1. So, that is equal to 2.5 volt. So, this 2.5 volt, it is coming to the VGS of transistor 2, and the corresponding current here, it is either we can use this information of 2.5 VGS, and then again you can use the similar kind of equation, or directly we can use the expression of this IDS2 current in terms of IDS 1 multiplied by W by L ratio of transistor 2 divided by W by L ratio of transistor 1. So, from this we can see that the IDS 1, it is 0.5 milliampere, and if you take the ratio of K into W by L and K into W by L here, in fact, we do have K in here and K in here. So, they are getting cancelled, and then W by L ratios are coming 4 by 1. So, that gives us IDS 2 equals to 2 milliampere. So, current flow here it is 2 milliampere. Now, we can find next part, it is that we need to find what is the minimum value of this VDS of transistor 2, particularly for transistor 2, for proper operation of the circuit. Namely, the current mirror current, output current can be well defined by this equation only when transistor 2 also in saturation. So, to keep this transistor in saturation, we know that the drain voltage, it should be higher than the gate voltage minus VTH, and gate voltage we know it is 2.5 volt. So, the VDS mean equals to VDS mean of transistor 2, it is equal to 2.5 volt is the gate voltage minus VTH, which is 1.5 volt. So, that gives us minimum requirement of this voltage, it is 1 volt. Now, let us consider the next part of the same question in the next slide. So, that will be continuation of this problem, but probably we can consider some finite value of this lambdas. So, in the next slide we do have, yeah. So, what we have here, it is all the other parameters remaining same. In fact, it is continuation of the same example, but we are considering lambda is equal to 0.01 per volt. And then again we can try to find what is the corresponding value of this current, and particularly for two cases, if VDS 2 here, it is 2.5 and 5.5. Now, you may recall from our previous calculation, the voltage here it is 2.5, VGS we already have calculated is equal to 2.5, and so that is also VDS of transistor 1. And then for the first case, if VDS 2 equals to 2.5, and if you consider this lambda, then you can get the current of IDS 2, which is having this equation W by L of transistor 2 divided by W by L of transistor 1 multiplied by I reference and then we do have 1 plus lambda 1 into lambda 2 into VDS 2 divided by 1 plus lambda 1 into VDS 1. Now, for this case VDS 2 equals to 2.5, both this VDS and this VDS they are same. So, and also the lambdas are equal. So, we can say that this part of this equation it is becoming 1 for 2.5. As a result, the corresponding current here it is coming. So, this ratio it is 4 and I reference, as I said, it is 0.5. So, that gives us 2 milliampere, and this is for VDS 2 equals to 2.5 volt. And let us try to calculate the IDS 2 for the other value, namely the VDS is equal to 5.5. So, for that, if I say VDS 2 equals to 5.5, for this IDS 2 it is equal to, so this part it is remaining same. So, we can directly write that part, which is 2 milliampere multiplied by this non-ideality factor 1 plus lambda 2 VDS 2 divided by 1 plus lambda 1 VDS 1. In fact, this part you can approximate by considering this denominator factor into the numerator factor, and then if we ignore lambda square term, and since both the lambdas are equal, so we can say that this is 1 plus lambda into VDS of transistor 2 minus VDS of transistor 1. So, what we are getting here it is 2 milliampere multiplied by so VDS 2 minus VDS 1. So, VDS 2 it is 5.5 and VDS 1 it is 2.5. So, this part it becomes, so this part it becomes 3 and lambda is 0.01. So, that gives us 1.03 is the non-ideality factor, and that gives us the current equals to 2.06 milliampere. So, we can say that for these two different VDS values, we do have different current. One is 2 milliampere here, another is 2.06. So, pictorially we may say that if we vary the VDS of transistor 2, the current here it is having a finite slope. So, this is IDS 2, and we do have one value here for 2.5 volt. The corresponding current is 2 milliampere. On the other hand, for 5.5 we do have, so this current is 2.06 milliampere. And from the slope of this line, we can calculate the output resistance, or we can strictly speaking it is small signal output resistance. So, to calculate the small signal output resistance, what we can see here it is we can get the calculate the slope of this line, and reciprocal of that is the small signal output resistance. So, small signal output resistance at the output of the current mirror R out. So, that is the voltage difference del V divided by del I, and we know that del V it is 3 volt, and the corresponding variation of this del I it is 0.06 milliampere. And so, this is giving us how much 1 by 2 into 10 to the power 5 ohms, right, or we can say this is 0.5 and then in fact 50 kilo ohms. So, that is the small signal output resistance of 50 kilo ohm, right. So, now if we continue this exercise for say other condition, so let us see in the next slide the third part of this. Now we are going to BJT. So, we have considered this simple current mirror. So, similar kind of circuit can be constructed by BJT. So, in the next slide we will be going for simple current mirror constructed by BJTs, and it will be having similar kind of exercise, but of course, the corresponding parameter of the BJTs are different. So, let us see in the next example how we calculate for current mirror circuit constructed by BJT. Now, in this example we do have Q1 and Q2, it is forming the current mirror, and in this case just for a change, instead of giving a reference current we are giving a resistor here. Supply voltage it is given to us 12 volt. This R bias resistor resistance it is 22.8 kilo ohm, and then we can assume that VBE on voltage for both the transistors are approximately 0.6 volt. In addition to that, we also have the information about reverse saturation current of the two transistors. So, Q1 it is having reverse saturation current of 9.5 into 10 to the power minus 14 ampere. On the other hand, for Q2 we do have reverse saturation current which is 2.85 into 10 to the power minus 13 ampere. In fact, if you see carefully, this is IS2 by IS1 is equal to 3. So, that is how I have picked up the number here. So, with this what we can probably we can see the mirroring ratio, it will be 1:3. If it is if we approximate that early voltage and then beta loss or the base current loss, it is ignorable, then we can say this current mirror is essentially 1:3 ratio current mirror. But before that we need to find what is the reference current itself, I reference. To get this I reference current, so we need to find what will be the I reference. I reference is equal to 12 volt VCC minus VBE on of 0.6 volt divided by 22.8 kilo ohms. So, we do have 11.4 divided by 22.8 K. So, that much of milliampere, which is 0.5 milliampere. Now, if I consider a simple situation, considering this, both the betas are very high, early voltages they are also very high, which means that non-ideality factor we are approximating equal to 1. So, the current flow here I C 2 is given by I S 2 divided by I S 1 multiplied by this I reference current, and then we do have the two non-ideality factors. One may be due to early voltage, another one may be due to the base current loss or due to finite beta. And for this part, both these non-ideality factors are equal to 1. So, this is equal to 1, this is also equal to 1. So, that gives us the current I C 2 equals to I S 2 by I S 1, which is 3, and then I reference current we have calculated is 0.5. So, that gives us the output current equals to 1.5 milliampere. Now, let you consider the effect of beta, namely the current loss due to whatever the currents are flowing here. So, that means this is no more equal to 1, and to get this non-ideality factor you may recall that this part is equal to 1 by 1 plus 1 by beta 1 plus I S 2 divided by I S 1 into 1 by beta 2. So, this is the non-ideality factor, and the values of beta 1 and beta 2s are given. This is also I S 2 by I S 1, it is also known. So, this is 3. So, we can say that, let me use this space. So, this non-ideality factor it becomes 1 divided by 1 plus 0.01, then we do have 3 here and then 150 in the denominator. So, that gives us 1 by 50. So, that is equal to 0.02. So, that gives us 1 divided by 1.03. Okay. So, with this factor, for this case, to calculate this current, we need to multiply by this non-ideality factor of 1.03. In fact, if you calculate it, what we are getting here, it is 1.5 divided by 1.03. So, that is equal to 1.456 milliampere. So, this part it is coming 1.456 milliampere. So, if I consider beta, finite beta, of course, this current is getting smaller because this non-ideality factor it is less than 1. On the other hand, if I consider say early voltage, if this voltage and this voltage they are not equal, then again we will be getting the second non-ideality factor. So, if this voltage it is higher than the VCE of transistor 1 or Yeah. So, in that case this second non-ideality factor, it may be higher than 1. So, to consider that, let me go for the third part of this example. So, in the next slide, it is continuation of the same numerical problem. So, as you can see here, we do have all the parameters we are keeping same, except we do have early voltage of the 2 transistors are given here, and intentionally we are using different values of early voltage. And we already have obtained the effect of beta, right. So, we already got I C 2 equals to 1.5 multiplied by 1 by 1.03, which in fact, so this is equal to 1.456 milliampere without considering this early voltage. Now, if we consider this early voltage, and if you observe the VC voltage difference, then we can calculate the that factor. So, let me consider V2, this V2, it is equal to 0.6 volt, and we know that this is VCE1 equals to 0.6 volt. So, if I consider this VB or V2 equals to 0.6, then that non-ideality factor, which is 1 plus lambda 2 multiply, sorry, I am going to MOS 1 plus VCE 2 divided by VA 2 divided by 1 plus VCE 1 divided by VA 1. And for this case, both this part is 0.6 and also this part it is 0.6. However, this early voltage we are keeping it is same. So, it is not getting cancelled, it is rather we do have 1 plus 0.006 in the numerator, and in the denominator we do have 1 plus 0.006 divided by 50. So, that is equal to 0.12. Okay. So, this non-ideality factor it is 1.006 divided by 1.006 divided by 1.012. So, this is 0.994. So, we need to consider this factor of 0.994, and so that gives us the current equals to 1.447 milliampere. This is the case with V2 is equal to 0.6. Now, if I consider say V2 is equal to 5.6, so in that case what are the changes do we expect? This part it will be different, namely that part it will be 5.6 divided by 100. So, that it becomes 0.056. In fact, this factor then it will be 1.056 divided by 1.012. So, that is equal to 1.0435. So, instead of 0.994, we need to replace this by 1.0435, and the corresponding current here, instead of 1.447, we do have 1.456 multiplied by this factor. So, that is equal to 1.519. So, this much of milliampere. So, for this voltage we do have 1.59 milliampere. Again, we can use this to data point to calculate the slope of the IC versus VCE. So, at this point of 0.6 volt VCE2, we do have the current. That current, it was this was 1.447. On the other hand, at this point we do have current which is for 5.6 volt VCE2, and this voltage, this current, it is 1.519 milliampere. So, again, by considering reciprocal of this slope, we can calculate the output resistance offered by this current mirror at its output. So, R out, so that is equal to del V, voltage change divided by the corresponding current change, and voltage change, it is 5 volt, 5.6 minus 0.6. So, that is 5 volt divided by this current difference. So, that is equal to 1.519 minus 1.447. So, that is 0.072 milli. So, that means it is 10 to the power 3 ohms, or we can say that this is equal to 69.4 kilo ohm. So, the small signal output resistance, it is 59.4 kilo ohm. So, now here we have considered, so far we have considered simple current mirror. Now, we can go for more precision current mirror, and as you can see here, if I consider finite values of betas and then early voltage, the ratio instead of 1:3, it is becoming different, slightly different though. There may be some precision cases, precision applications where this much of difference may not be still acceptable, and then we can go for betterment of the circuit. So, for current mirror constructed by BJTs, we do have two types of improvement. One is to take care of the non-ideality due to the early voltage. Another one, it is to take care of the non-idealities factor due to the base current loss. So, to take care of the base current loss, as we have said that we can have a beta helper circuit here, so that the current loss to the base of this third transistor, which is much smaller than whatever the base current is going to Q1 and Q2, which is referred as beta helper. So, continuation of this numerical example, to go for that beta helper, let we go to next slide. So, it is, I should say it is more like a continuation of the previous problem, namely we are retaining the parameters here. So, the current flow here it is 0.5 milliampere, and we have calculated the base current, the non-ideality factor due to the base current loss. Now, we can improvise the circuit by using beta helper here. So, let you call this is transistor 3. So, we are adding this beta helper, and this beta helper its beta it is 99, and then once we add this transistor, we need to readjust this resistor, because once we add this transistor, since the collector and base voltage they are not same. In fact, if you observe carefully, this is one VBE, this is another VBE. So, if I approximate that this VBE it is also 0.6, then the DC voltage coming here it is 1.2 volt. Okay. Now, since you are trying to keep the focus only on the non-ideality factor coming due to the base current loss, we are suppressing the other information, namely in this example we are considering early voltage it is very high, and we are primarily focusing on this base current loss. So, in the next slide we do have the beta helper circuit. So, here we do have the beta helper circuit drawn for you. We do have Q3 here, and as I said that this is approximately 0.6, and here also it is approximately 0.6. So, we do have 1.2 volt. So, what we are doing here to retain this current of 0.5 milliampere in this numerical example, we are readjusting this R bias to 21.6 kilo ohm, and that gives us the I reference current, it is same as 0.5. So, let us see that our I reference equals to 12 volt minus 1.2 volt here divided by this R bias, and so this is equal to 10.8 10.8 divided by 21.6. So, that gives us 0.5 milliampere. So, for our comparison, better comparison, we are keeping this reference current same as the previous case, and then we can calculate the corresponding non-ideality factor. So, you may recall the non-ideality factor in presence of the beta helper is, so non-ideality factor it becomes 1 divided by 1 plus 1 by 1 plus beta 3 multiplied by 1 by beta 1 plus I is 2 divided by I is 1 multiplied by 1 by beta 2. And earlier we have calculated in absence of this one. Now, we do have 1 plus, so this part 99 plus 1, so this is 100. So, that gives us a factor here 0.01 getting multiplied with beta 1 it is 100. So, 1 by beta 1 it is 0.01 plus this one it is 150. So, that is equal to 0.02, right, and so this is how much, this 0.03. So, that is equal to non-ideality factor. So, it becomes 1 divided by 1 plus 0.0003, and this is very, very small compared to 1. So, we can approximate that this is equal to 1. In fact, how much is it coming? This is 1.0003 reciprocal. So, that is equal to in fact 0.9997. So, that is how this beta helper is helping us to maintain this ratio here. It is very close to 1:3. So, similar to, so this circuit, as I said that it is improvised current mirror. Similar to this improvisation, we do have different improvisation by adding something called cascode transistor to make the non-ideality factor due to early voltage, it will be very small. So, we will be discussing that circuit, but before that let you take a break and we will come back. Thank you.